Good evening, everyone. My name is Amit. This is week 9 for electronics part of GATE Physics Live session. For the past 2 weeks, we have been doing digital electronics, and this week we'll continue with digital electronics part. Today we'll be doing JK flip flops and their applications in counters, and then we'll move to ADC converters, analog to digital converters. As always, we have a few questions from the GATE previous year questions. I'll go along with them. I'll explain the concepts and then we'll look at the questions. Because the concepts are related, so it helps that more than one questions are based on the similar concepts, so we get to revise the concept again as we go through with the questions. I'll wait for one more minute and then I will start our session for today. If you have any comments about the last session or this session, please feel free to stop me anytime. All right, we'll wait for one more minute and then we'll start. All right, let's begin. I hope I'm audible. Yes.
Yes, sir.
Okay, so I'm going to share the presentation now. Is the screen visible?
Yes, sir.
Full screen?
Yeah.
Okay. So today's topic is concerned regarding counters, and before we go ahead with counters, we need to understand a building block of the counter, that is the JK flip-flop. Now, even before we understand what a flip-flop is, we need to talk about a couple of terms here, and I'm going to write these terms here so that we are all on the same page. Just a second. Yeah, so essentially there are two kinds of circuit then that we come across as far as digital electronics is concerned. One is the sequential circuit and one is the combinatorial circuit. Now, what is the difference between the two? And it's a very simple difference, and just by looking at the circuit you can understand, you can say that it's a sequential or combinatorial circuit. A sequential circuit will always have a clock. That's the very basic thing, that if your circuit has a clock, it will be most likely sequential. Sometimes it's not explicit whether it's the clock is there or not. It's not explicit. For instance, if you look at the circuit of a JK flip-flop, you will not even see a clock, but since it's a sequential circuit, so even though this is a simplistic definition, a more truer definition of a sequential circuit is that output will depend on present input and past input. Now, this is important. In combinatorial circuits, output depends on present input. It doesn't care what was the value before. Sequential circuits do, depending on how the circuit looks like. So sequential circuit will depend on some past value. May depend, I'll not say will, it may depend on some past value, whatever the circuit, whatever the value was. And we'll see, we'll look at the ripple counter, which is a type of a sequential circuit, and we'll get to see that what I mean when I say that, right? So let's just, for the sake of discussion, let's assume that this is the definition of a sequential circuit, and usually you will see clocks. This input is the most common feature which you rarely find in combinatorial circuits. you invariably find a clock in the sequential circuits. The word, as the term suggests, sequential comes from the word sequence, and the English word sequence means one after the other. There is a series of steps happening. First thing is happening, and then second is happening, and the third is happening. So naturally the second step will be dependent on first step. Similarly, the third step will be dependent on the second step and on the first step. That's what we mean by sequential circuits. And this is captured by a step is defined as a clock. So what step to take when a clock edge is there, falling edge or rising edge. So I'll draw a clock here. So this is how a clock looks like. So this is 0, this is 1. This is called the rising edge. Why rising edge? Because the clock input is rising from 0 to 1. Hence this is called as rising edge. Similarly, when the output falls from 1 to 0, this is known as the falling edge. As the name suggests, the clock value is falling from 1 to 0, and usually circuits are dependent on the edges, or they may be dependent on the value. So this value is high. When the clock is high, some circuit may be turned on. When the clock is low, some circuit may be turned on. In effect, sequential circuits depend a lot on the clock and what is the value of the clock. Okay, we'll see that in our example. So this is just the theory part. When we come to the examples, then it will become more clearer. Now, in this table you can see the truth table. I have already defined, we've already seen the past two classes what a truth table means. So a truth table is nothing but the combination of all the possible inputs. We write on the input side and then we try to calculate the output. It's very straightforward. So we write the inputs and then we write the output. So for instance, in a JK flip-flop, there are two inputs, J and K, and since it's a sequential circuit, the clock is also an input. So sometimes you do not see clock as the input, so you only see in the textbooks or in some videos you will only see J and K as the inputs and not the clock. But here, for the sake of completion, I'm also adding the clock, but for the time being, let's just forget about the clock and let's just look at only at this part, the one which I am highlighting in the red rectangle, hand drawn rectangle. Now what does it say? The output we have defined as Q. So usually you will see the outputs here defined as the value with the English alphabet capital Q. It can be anything, but this is the notation that has been followed. Now what does it say? When the value of J is 0 and the value of K is 0, the output Q remains Q. Now what is Q? Q can be any value, 0 or 1. Okay, so what does this say? This says when the value of J is 0 and the value of K is 0, the output Q will remain as it is. So if the earlier value of Q was 0, so again it will remain 0. If the earlier value of Q was 1, this will remain to be 1. Now note that the output here is dependent on the inputs J and K as well as the previous value of Q. Okay, similarly, if the value of J is 0, the value of K is 1, the value of Q will now become 0. On the other hand, if the value of J is 1 and the value of K is 0, the output will become 1 now. And finally, if both the inputs are 1, then the output will invert itself. So for instance, let's say J is equal to 1, K is equal to 1, and let's say Q's value was 0. So we denote it as Qn. This means the previous value of Q. Now we know that when J is 1 and K is 1, Qn plus 1, this means the new value of Q is denoted as Qn plus 1, will be nothing but Qn bar. Okay, when J is equal to 1 and K is equal to 1, Qn plus 1 is equal to Qn bar. Okay, so I can also say this is, let's say, Qn plus 1. This is the next value of Q. This is Qn, this is Qn bar. So that's how we see the value of Qn plus 1 will be, if J and K both are 1, will be nothing but Qn bar. So what's the previous value of Q? That was 0. So now Qn plus 1 will become 0. Note what is happening. This symbol that you see is called toggle. Why toggle? Because when Qn is 0, the next value will become 1. And now let's take this case. J is equal to 1, K is equal to 1, and Qn is equal to 1. Let's take this case. Again, we know when J is 1 and K is 1, Qn plus 1 will become Qn bar. What's the value of Qn bar? Qn is 1. In this case, it's 1. 1 bar is 0. So what's happening? Original value of was 1 and final value is 0. So what's happening? 1 to 0. The value is toggling. In this case, it was toggling from 0 to 1. So what we see is that when j and k both are high, right, the next value of output will simply toggle as compared to the previous value. Hence, this condition is also known as the toggle condition. Note that when j is equal to 1 and k is equal to 1, the next output is nothing but the inversion of the previous output. And I have shown you in both the cases this is true. Hence, this is also known as the toggle condition. Now, this is a very important condition since this is used to create what is known as ripple counters. The ripple counter. We'll see what each term means. Counter means something which counts. So it can count from 0, 1, 2, 3, 4, 5, 6 and so on. It's a ripple counter. Ripple counter means, ripple means a disturbance. So what happens is that the value would be 0, then the value will become 1 and 2 and 3 and 4 and so on. This is what is referred to a ripple. So a small disturbance. Note that the value is not changing drastically from 0 to 7 or something. No, it's changing small. 0 to 1, then 1 to 2, then 2 to 3. These are ripples, small increases. Hence this is called as ripple counter. Why 4-bit? Because there are 4 outputs. You see Q0, Q1, Q2 and Q3. So in this circuit what we have is this is the circuit diagram of a ripple counter. We'll solve this. Don't worry. Don't get disturbed by just seeing the circuit. It's a very simple circuit. It's just that there are 4 flip-flops. So hence it's called 4-bit ripple counter. And there are 4 outputs corresponding because each flip-flop has one output, Q. Right? Look at this first flip-flop, then second, then third, and then fourth. The good part, why ripple counter circuit is that the 4 flip-flops, the output of first flip-flop is the clock of second flip-flop. Note this. Let's name this flip-flop 1, 2, 3 and 4. The output of JK flip, okay, so let's count it 0, not 1, 2 and 3. Okay, so the flip-flop output of JK0 is the clock of JK1. Similarly, the output of JK1, which is Q1 here, is the clock for JK2. You can see here. And similarly, the output of JK2 here, Q2, is the clock for JK3. This is how the circuit diagram for a ripple counter looks like. And we have seen that when both the inputs are high, both the inputs J and K are high, then JK flip-flops behaves like a toggle flip-flop, which means it will toggle. Every time the clock comes, the output's value will toggle. Right? So this is the circuit. 4-bit counter constructed out of 4 flip-flops. It is formed by I just explained this circuit to you, which is written in which is written over here. And the input is nothing but a series of square pulses, which I told you. Clock is usually a series of these pulses. And this is important. Change of state is triggered by falling edge. This means whenever a falling edge comes, like this edge and this edge, or this edge, or this edge, the outputs will change, right? And we are required to find the output at this stage, at the stage T1. I'll again summarize. This is the circuit of a ripple counter in which 4 JK flip-flops are used. The circuit is arranged in such a way that all the inputs J and K are set to 1. You see this, set to 1, logic high. This means every flip-flop will toggle at the falling edge. Why? Because the question says so. So whenever a falling edge comes, the output of JK flip-flop will toggle. Okay, and we are required to find the output at some time T1. So we'll go ahead and do that. This is the circuit diagram. I've just drawn it again. Now let's forget about anything and let's just look at the output of Q0. So I'm writing the truth table for this JK flip-flop. So I'll write J0, K0, and the output is, let's say, Q0 n plus 1. Okay, this means n plus 1th state. And we know this is 1. Right, because both the inputs are 1, and I know that the value of it will be Q0 n toggle. So whatever the previous value is, the next value will toggle. So let's just draw the value of what will the Q0 look like. Okay, what will Q0 look like? We are given that initially Q0 equal to 0. Okay, let me draw it again because this doesn't look good. Okay, right. So this is q naught, right? And we have seen that q naught n plus 1 will be nothing but q naught n toggle. Why? Because this is a toggle flip-flop. We saw that, right? So we know that the initial value at time t is equal to 0, it is given that q naught value is 0. So let's just write that with a different pen. Okay, so this is the value. So at t naught the value is 0, and the value will remain 0. Note that any change will happen just at the falling edge. Okay, so this is the falling edge, again this is the falling edge, right? Because this is the clock for this flip-flop. Okay, so this is how it will look like. So it will remain 0 till here. Now what will happen is that at this clock edge, at this edge, we know that the state should change according to this relation. So now the new state q naught n plus 1 will become the inversion of q naught n. So if the state is 0, it will simply become 1, and it will remain 1. It will remain 1 until what time? Till the next edge. What happens in the next edge? Same thing happens. It will invert, because this is still, j and k are still connected to 1. If it is 1, then this means q naught will toggle again. This means it will become 0. It will remain 0 until when? Until the next clock edge, next falling edge. What will happen? Again it will invert. So it will again become like this, and it will continue like this, and then this, and then this, and then finally this. So now we notice that at time t1, this is the time t1, we are required to find the value of q naught at time t1. So the value of q naught at time t1 is 0. So we'll see the options. Q naught should be 0. So this option is eliminated, option A. Option C is eliminated. So either it's B or D. Okay. So now let's calculate the value of q1, right? So again I'll draw the value q1. Okay, simple. Let's draw q1 now. I'll use now green color. Okay, so now look at q1. What is q1? Q1 is the output for this ripple counter. Let's say j1, k1, and this is q1, right? So again we'll write, since again this is a jk flip-flop, so again the truth table remains the same. j1, k1, q1 n plus 1. If both are 1, q1 n plus 1 will be nothing but q1 n toggle. We saw that in the truth table in the previous slide, right? So again we can simply write q1 n plus 1 will be nothing but q1 n toggle, right? So it will toggle at every falling edge. Now note that the clock for this flip-flop is q naught. Okay, so we have to take the falling edge now of q naught, which is this. So we have to take these edges now. Okay, we have to take these edges. Okay, we'll take these edges. So initially it is given q1 equal to 0. q1 is 0, fine. When will it change? It will change only at the falling clock edge. So this is the clock for this flip-flop 1, right? So what will happen? It will toggle. So it will toggle and it will become 1 simply. It will remain 1 till this time. Then again a falling clock edge comes, and then it will toggle again. So it will become 0. Then again this falling clock edge comes, it will become 1. And then again this falling edge comes, it will become 0. So this is the time we were required to find out. This is t1. This is time t1, note that. So q1 is also 0 at time t1. Okay, so let's see. q1 is 0. So option B is the correct one, right? So we found q naught equal to 0, q1 equal to 0. Now if I go ahead, I can simplify q2 also. So let me do that. Let us complete this circuit. Let us complete this question. So this is how it looks like, right? This is q1. Now I'll draw q2. I'll draw q2 in red pen. q2. Let's draw q2. Now note that for q2, again the same thing happens. This is the jk flip-flop. Again the toggle condition will be true. So I can again write q2n plus 1 will be equal to q2n bar. And what is the clock for this? Note that the clock for this flip-flop is nothing but q1. So whenever Q1 falling edge comes, the output will change only then. And initial value is 0. It is given. Q2 initially is 0. This is here. So Q2 will be 0 initially. This is 0. When will it change? It will change only at the falling edge. So it will become 1. It will remain 1. It will change when again? Again at the falling edge, this edge, it will become 0. So it has become like this, and we are required to find, this is the time t1. So at time t1, Q2 is equal to 0. So Q2 is 0, this option, right? Now let's complete the final part now. In the final part, I'll take blue pen again. In the final part is Q3. Again, Q3 is JK flip-flop, right? So again, with inputs, both inputs are 1, this means it will toggle. So I can write Q3n plus 1 will be nothing but Q3n bar. Now this condition, now what is the clock for this flip-flop? Clock for this flip-flop is nothing but Q2. So we have to check the falling edge of Q2, which is this. And we know that initially Q3 is given equal to 0. So Q3 will become 0, and it will change only when this edge comes. So this edge comes here, it will become high, and it will become, and we are required to find the value of at time t1. This is time t1. So at time t1, the value of Q3 is high. This is 1. So the option here would be this, Q3 equal to 1. So we have seen that Q0 equal to 0, Q1 equal to 0, Q2 equal to 0, and Q3 equal to 1. So this is the circuit. This was the circuit of the ripple counter that we saw here, and we found that the correct answer is B. So this is again, I'll summarize what we have discussed in this question. We discussed what a JK flip-flop is. So we saw the truth table for JK flip-flop, right? Qn plus 1. We saw that, and since both the conditions are 1, so we just took the last row which says Qn bar. This thing. This is called the toggle condition. Toggle condition because output flips at every clock edge. So what is the clock edge? In the question it was given triggered by the falling edge. So whenever a falling edge comes, the output changes. Now we saw that the output of one flip-flop was the clock for other input. So we solve this circuit like this. We first find out Q0, which was the clock for Q1. So we took the falling edge of Q0. Then for Q2, the clock was Q1, and we took the falling edge of Q1. Then for Q3, clock was Q2. You see this is connected. We took the falling edge of Q2, and then finally we solve the circuit, and we find out the option B is correct. So that's how it is. It's very simple. If you just follow it, this was just based on just this truth table and nothing else. If you remember the truth table for JK flip-flop, you can solve a question of ripple counter. Now it just remains a problem of simply drawing the waveforms, which is straightforward. Now this is a very interesting question. We are required to find the number of flip-flops required to construct a mod 75 counter. Now here mod 75 means modulus 75. Modulus means nothing but taking percentage. So when you take the percentage with the divisor 75, you can count from 0 to 74, right? This means that your lower value should be 0 and maximum you can get is 74, right? So I told you that every bit in ripple counter, one bit is equal to one flip-flop. Right? Now we need to represent the decimal number 74. Now if we try to represent the decimal number 74, okay, 2 to the power 6. 2 to the power 6 is 64. Yeah. So if you use 6 bits, you can go only up to 63. For instance, the maximum number in 6 bits is this. This turns out to be 63. But we are required to go to 74. Hence, we need to add one more bit. So it can so if we add 7 bits, then we can count to 0 to 127. But we need to only count to 74. So that's fine. We'll stop at 74. But we require at least 7 bits. We require at least 7 bits for the decimal number 74. Now each bit corresponds to one flip-flop. I told you one bit is equal to one flip-flop, and we saw in this example. So one bit. So these are the bits, right, of ripple counter. One bit was equal to one flip-flop. So again, we require 7 bits to represent number 74, and hence the number of flip-flops required is 7. So we need 7 flip-flops to represent a mod 75 counter. So this is the answer for this. Right. So we are finished with JK flip-flops. Do you have any questions till now or comments? Do you want me to repeat something? Because now we are going to start analog to digital conversion. So if you have any doubts, please feel free to ask. Want me to repeat some concept, some like some how is the clock changing, or what is a falling edge? Just please ask me.
Yes, sir. Can you explain again flip-flop?
You want
I
me
didn't
to
get it.
you want me to explain flip-flop?
Yes, sir.
So this is the flip-flop. As I told you, just look at, so this is the truth table for a flip-flop. Just look at this condition. This is the truth table for a JK flip-flop. So what happens is that when both the inputs are 0, the output will remain the same. So this is Qn plus 1 and this is Qn. Qn means the previous state. Qn plus 1 means the coming state. So when both the inputs are 0, the new output is the same as previous output, right? If both the inputs are 1, the new input Qn plus 1 is nothing but inversion of Qn, means it is inverted, it is toggled. This is called toggle condition. So let's say when j is equal to 1 and k is equal to 1, and let's say Qn is equal to 0, right? So what will happen according to this? Qn plus 1 will be Qn bar, which is 0 bar, which is 1. Or it can happen that initial state was 1. Then again the formula remains the same. Qn plus 1 is equal to Qn bar, which means 1 bar, which is equal to 0. So we note that the initial state was 0, it became 1. This is called toggle. If the initial state was 1 and the final state becomes 0, this is again what is called toggle. Hence, when the condition j is equal to 1 and k is equal to 1 for JK flip-flop, we call such condition as the toggle condition. And in this question, we were given JK flip-flops where both j and k were 1. Note this, both j and k are 1 here, right? So all these flip-flops are in toggle mode. Hence, whenever the clock edge comes, so here it's given falling edge. So whenever the clock edge comes like this, like this, like this, the output of this flip-flop will change. So we saw that when this edge, when the clock for first flip-flop, look at this flip-flop J0, this one, when the clock for this flip-flop fell, the output of Q0 changed. It was 0, so it toggled it, it became 1. When again the falling clock came, it again toggled from 1 to 0, and so on. And this happened for all the flip-flops, and hence we finally got these 4 or 5 waveforms. Okay, is it okay now?
Yes, sir.
Okay. So, and then we saw the flip-flops required. This is simply nothing but the your decimal to binary conversion. You simply convert whatever the mod is. So we need 0 to 74, right? So you convert the 74 in binary number, which comes out to be which is represented by 7 bits, because 63 is the maximum 6-bit number. Okay, so for 74 we will require 7 bits, and 127 is the maximum 7-bit number, and 63 is the maximum 6-bit number, and 74 lies somewhere in between, right? So 74 will not be satisfied by 6-bit, but it can be satisfied by 7-bit. And we know in ripple counter 1 bit is equal to 1 flip-flop. So we require 7 bits for 74. This means we require 7 flip-flops for counting 74. Okay. Now we come to something called analog to digital converters. Now before we need to just simply understand that why was this required, analog to digital conversion. In our lives everything is analog, right? The you are hearing my voice, this is analog. I'm not speaking in zeros and one. My voice is going down, I'm slowing down, so everything is analog. The temperature that you see around you, right, it's not analog. That is not like 0 Kelvin one day and it's 300 Kelvin the other day, or 0 Kelvin during the night, 300 Kelvin during the day. No, it's not like that. It varies, right? It varies. So it's analog. They cannot be just simply to zeros and ones. But on digital side, we have the computers. Unfortunately, they only understand zeros and ones, but here the value is huge. let's say 0 Kelvin to 300 Kelvin. There can be infinite number of values here, and if you take the only whole numbers, then still there are 301 whole numbers. How will you represent 301 whole numbers in just 2 bits, in just 2 numbers? So we need to, in order to save the data for temperature, we need to convert this analog signal to a digital signal, and that's the job of a to D converter. This is how it's written, AD converter, or you can see ADC, analog to digital converter. So in order to represent, in order to store the real life analog values, we need a converter which is called an analog to digital converter. Now, one of the most important parameters in an analog to digital conversion is the resolution, and we'll see what the resolution means, right? So what we need to do, we need to convert an analog input to a digital output. I just introduced that thing to you. Now let's say there are so for any analog input, let's say that there are 2 values, right? Let's call this the minimum input. So let's say this is temperature, so let's say this may be 0 Kelvin, and let's say it has a maximum input. So let's say the maximum input, for the sake of example, let's say it's 300 Kelvin, right? Correspondingly, there will be a minimum input and maximum output, correct? So now let's say again, let's say the minimum input is Vmin and the maximum output is, maximum input is Vmax. So what is the difference? The difference is Vmax minus Vmin. Similarly, on the other side, let's say the minimum output in a binary case can be 0. You cannot go lower than 0. So the minimum value that you can store is 0. The maximum value which you can store, depends on the number of bits you can store, is 2 to the power n minus 1, and the difference comes out to be 2 to the power n minus 1. So I'm simply just subtract these two numbers. So the range here is Vmax minus Vmin, and the range here is 2 to the power n minus 1. Simple, right? And these must be equal. Why these must be equal? Because digital output is not something that is independent of input. This is a one-to-one conversion. So whatever Vmax minus Vmin is, the range here should be exactly equal to the range that we are storing. It's very simple, right? So now we introduce the definition of resolution. The resolution is the minimum value that can be distinctly measured. Now, for instance, I'll give you an example. The resolution of a human eye is something of tens of nanometers, let's say 50 microns, right? So this means a human eye, your eye and my eye, can distinguish 2 objects which are 50 micron apart. If you see any metal, the distance between the 2 atoms there is a few angstroms, right? We cannot distinguish the 2 atoms separately because the distance is simply 1 angstrom, and our eye can only distinguish 2 objects when they are 50 micron apart. So that is the meaning of resolution, the minimum value that can be distinctly measured. In this example, in the example that we are talking about, this means that 1 bit change. So let's say the value here was something 0, 1, 1, 0, and so on. So these are some bits and these are some bits, right? So 0, 1, 1, 0 was the value. Now the next value can only be 0, 1, 1, 1. Only 1 bit change, right? Only 1 jump. Then only we are able to measure. So this is called resolution, right? Only when 1 bit changes, then only we'll be able to capture the change in the input. So input is also changing. Input is analog here, something like this. And we want to capture this, right? We can capture only when the 1 bit changes here, at least 1 bit changes. So if we want to find note that we need minimum value. So this means when only 1 bit changes, right? This is what I have written here. Now we know that 2 to the power n minus 1, we just saw 2 to the power n minus 1 steps here. There are distinct levels. 2 to the power n minus 1 steps is nothing but Vmax minus Vmin. We just saw that because this is nothing, output is nothing but representation of input, right? Simply by unitary method, we can say that this implies that 1 step equal to Vmax minus Vmin over 2 to the power n minus 1, right? And note that this is nothing but the definition of resolution. That if you take one step from here to here, only 1 bit change, that is your resolution. Okay, so this is the formula for resolution which you can try to remember. Now we'll come back to the question. So it says that we have a 7-bit A to D converter. This means n equal to 7. Okay, and 5 volts full scale. This is the input, right? This is the input. So V max is 5 volts. Now what is V min? Okay, the question is silent about V min. What is V min? There's no V min. Then if nothing is given, assume V min equal to 0. This is most often the case because there is some reference voltage which is usually 0. So again, if not given, we'll assume V min equal to 0, right? So the best resolution we are able to find out, now we find that resolution, we just saw the formula. Resolution is nothing but V max minus V min divided by 2 raised to the power n minus 1. So V max is 5, V min is 0, the value of n is 7, so 2 to the power 7 minus 1, so that is 5 over 2 to the power 7 is 128 minus 1, 5 over 127. And now I have to get my calculator. So this is coming out to be 0.039 volts. Oh, it's in millivolts. Okay, so this is coming out to be 39.37 millivolts. So up to 2 decimal places, yeah. So we have found out up to 2 decimal places, so we can simply say 39.37. It's a very simple question and just one formula based question, and not just formula. I explained you the reasoning behind how we came to this formula. So yeah, someone raised their hand. Gangadhar, yeah, please go ahead. You have a question?
Yes, sir. Sir, can I please explain, sir?
Which part? This thing?
This full scale. What is the meaning of full scale?
Full scale is nothing but, okay, see,
Yes.
full scale is nothing but that this full scale means that this 5 volts is the V max. That is the meaning of full scale.
Yes.
Okay.
Sir.
Yeah.
Okay, sir. Sir, it's a small doubt, sir.
Yeah, please ask.
A by D converter with 5 volts.
Yes.
What is the meaning of this one, sir?
A to D converter means the input will be analog.
Yes, sir.
Input is analog and output is digital. This is the
Yes,
meaning of analog to digital converter. A device which does this thing is called A to D converter. AD converter.
Yes,
Full scale means
sir.
Yeah.
Sir, a problem clarity కొద్దిగా లైన్ స్టెప్ బై స్టెప్ కొద్దిగా ఫస్ట్ నుండి లాస్ట్ వరకు కొద్దిగా చెప్పుకొని వెళ్ళిపోండి సార్.
I'm sorry, I'm not able to understand. Can you speak again?
Step by step can explain, sir. Starting నుంచి ending.
That's what I did, right? Okay, I'll do it again. So in the question we were given n equal to 7. Okay.
Yes,
n equal to 7. V max is 5 volts, which is given. Full scale means this is the V max, 5 volts. Okay.
Yes, sir. Okay.
V min is not given, but we'll assume that V min equal to 0 volts.
Yes.
And the formula for resolution is resolution equal to V max minus V min divided by 2 raised to the power n minus 1. Okay. Here is the formula for resolution.
Yes, sir.
Now you put the value of V max as 5, you put the value of V min as 0, you put the value of n as 7. So you get 5 minus 0 upon 2 to the power 7 minus 1. 5 minus 0 is 5, 2 to the power 7 is 128, so you get 5 upon 128 minus 1, which is 5 upon 127. And when I did the calculation, it came out to be 39.37 millivolts. Okay? Is it okay? Am I audible? Others?
Sir, he left class.
Oh, okay. Okay. Shall I go ahead?
Yes, sir.
It was unfortunate. Okay. Right. So this is now the second question. Again, the same concept. Again, we have analog to digital converter. Now it's given that it's 3-bit. Okay. So 3-bit. I'll write n equal to 3. It's ranging from 0 volts to 10 volts. So very good. V max is 10 volts. V min is...
Sir, your screen is stopped.
The screen is stopped? Okay,
Yeah.
I'll share again. Sorry. Is it visible now?
Yes.
So what do you see? Can you see n equal to 3 written?
No, sir.
Okay, this is very strange. But my voice is audible.
Yes, sir.
Okay, I'll share again. I'll share again. What do you see now?
Nothing.
Okay. Is there anything visible?
No, sir.
Okay, I don't understand what's happening. Just give me a minute. I'm sorry. Since when did the screen go out? Did you see the previous question completely about the resolution question?
Yes, sir.
Okay, I'm trying to fix it. Sorry, fellows. Sorry.
Not see. Okay.
Anything now?
Mm. A.
Sorry.
Nothing, sir. Nothing to see.
Can anyone else also say that if they're able to see anything? Whom am I talking to right now? Pratik. Can anyone?
Now,
Sorry. Aishwarya.
It's visible.
it's visible.
Okay, ठीक है. Pratik, I think you may want to refresh your condition or internet connection, or just leave the meeting and join again. I'll admit you. Okay, just try doing that. All right. So I hope you're able to see my screen. Other people, yes. Aishwarya, Rajiv.
Yes, sir.
Okay. So I'll start with the question now. So again, this is a to d converter, and we are given n equal to 3. It's here, and we are given Vmin is 0. In the last question, Vmin was not there. Here it's explicit. Vmin is 0 and Vmax is 10. Vmax is 10 volts. Okay. Now we need to find out the value of that if an input is 6 volts. Okay. So let's say, so I'll again draw this diagram that we saw earlier. So this is 10 volts. This is the left side is input. This is 0 volts. Okay. This is your input side. In the output side, I'll draw using a different pen. So on the output side, we have 3 bits. So maximum 3 bit number is 111, correct? And minimum 3 bit number is 0. So this 0 corresponds to this 0. Similarly, 111 corresponds to 10. Now again, we'll simply first find the resolution as always. Resolution is Vmax minus Vmin over 2 to the power 7 minus 1. So Vmax is 10 minus 0. Sorry, 2 to the power 3. Sorry. So 2 to the power 3 is 8 minus 1. So that's 10 by 7, and that comes out to be around 1.43. So 1.43. So what does this mean? Now that resolution is 1.43. So what does this mean is that if first step is 0, the next step would be 1.43. Sorry, the next step, sorry, my bad. I wanted to draw it on the other side, right? So what does this mean is that, so we found out that the first step is 1.43. so this is the first step, 1.43. This corresponds to 001. Note that the first step, the bottom is 000. This is 000, 3 bits. Note that it's a 3 bit converter. So the first, the lowermost the floor is 000. After that it will come 001. The corresponding value here would be 1.43 volts. Okay. Now what will the next step? The next step here would be 010, because after 001 comes 010. Similarly, the next step here would be 2.86 volts, right? Because 1.43 plus 1.43 is 2.86. Now, what will your third step now? Third step will be, in black, would be 1.43 times 3. So that will be around 4.3 volts. Again, here it would be 011. Note that I'm jumping only one bit. So this corresponds to 0, 1, 2, 3, so on, right? The next comes out to be 4.3 volts, and which is 0 1 1. And finally let's draw one more, this time in orange. So next so this will be one, so I'll add 1.43 in this, so it will be 5.73, and the value here will come out to be, so the next step after 0 1 1 is 1 0 0. And let's draw one more level now. I've almost run all the levels, it's fine. So this will come out to be now, so 5.73 plus 1.43 would be that would be 7. This will be 6 and 4, 7.16, and corresponding level here would be 101. Now the question says that we need to find the output with respect to the input of 6 volts. Now look carefully, 6 volts will lie somewhere here, right? 6 volts will lie somewhere here, and it's a 1-to-1 conversion. So if 6 volts lies between this level, the orange level and green level, this means 6 volts will lie somewhere here, correct? Now note that here they can be continuum of values, here it cannot be, it can be, it's like this, it's a step. So 6 volts will lie on this step, it has not reached here, so it has reached here but it has not reached here. So this means 6 volts which correspond to the value of 1 0 0, not 101. Why? Because it has not climbed that step, it has only climbed up to here. So it starts climbing from 0 0 0, then 0 0 1 and so forth and so on. It has only climbed up to 1 0 0, and hence the value corresponding to 6 volts would be 1 0 0. So is there an option? Yeah. So this is the option. Option C would be the correct one, 1 0 0. Is it clear? I'll just summarize it again. So we were given a 3-bit converter, so with n equal to 3, and with the maximum min values were given for the input, and we find out what is the resolution. We found out the resolution is 1.43 volts. Okay, this means that the first step would be 1.43 volts. This means the first step after, I told you, one step equal to the resolution. So what is the first step after 0 0 0? Is 0 0 1. So this is the first step, so it corresponds to, it is shown in green. Now the second step is in yellow, which is 0 1 0, and will correspond to 2.86. And similarly we drew all the levels, right? And we find out that if the input is 6 volts, which is here, it has reached the level of orange. So it has reached the level of orange, but it has not reached the level of light green, and hence the answer would be corresponding level of orange, which is 1 0 0 here. Okay, now this is an interesting question. What we are given here is again an A to D converter, but this time 6 bits. So again I'll write n equal to 6. Now in this question we are not required to find the resolution, Vmax, Vmin, nothing like that. We are required to find what is the maximum, if the maximum conversion time is 32 microseconds, sorry, what is the clock frequency? Now we'll see this in a minute. So let me just change my pen, right? We just saw that the output changes like this. We just saw that it's in steps, because it is a digital output, it's not an analog output, right? So let's say this is the value 0, so this is 1 2 3 4 5 6. Let's draw one more level. Let's say this is the value of 1 1 1. Am I correct? So this is 1 2 3 4 5 6. Yeah, I'm correct. So this is how it looks like, right? So now what it's saying that in order to jump from the 0th level to the first level, okay, when you jump from here to here, there is an internal circuitry involved, right? It takes one clock cycle. If you jump from here to here, another clock cycle. Here for here, another clock cycle. This means if you have n bits, I'm talking about only this. Remember that there are different types of ADCs, counter type, dual slope, and whatnot. There are many types, but we are talking the simplest converter, which is counter type ADC. So what's happening is that for each step it requires one clock. So if let's say there are n bits, this means the total number of outputs can be 2 raised to the power n minus 1. Why? Because we know that the maximum value can be 2 to the power n minus 1, and it will. So now every step requires one clock cycle. This means that if we want to go from 0 to the maximum value, which is 2 to the power n minus 1, this means we require 2 to the power n minus 1 into t clock. This is the time that you require. Note that To climb one step, you require a second. To require one step, you require one clock cycle, right? When you have to climb 2 to the power n minus 1 steps, clearly you require 2 to the power n minus 1 times t clock. This is the maximum time. So you either minimum value that you can have is 0. We saw in the first slide, right? The minimum value is 0, maximum value is 2 to the power n minus 1. So what is the maximum thing that you need to convert? You are at value 0 and you want to go to the maximum. So what is the time that you will take? You will take 2 to the power minus n minus 1 into t clock. And this is given in this question, 2 to the power n minus 1 times t clock has been given as 32 microsecond. N is also given, n is 6. So we'll get 2 to the power 6 minus 1 times t clock equal to 32 microseconds. 2 to the power 6 is 2 to the power 6 is 64, minus 1 is 63. 63 times t clock equal to 32 microseconds, and this implies t clock equal to 32 by 63 microseconds, which is approximately equal to 0.5 microseconds. Now we have just find out that what is the time period of the clock, and we know that the frequency is nothing but 1 over time. So this is 1 over 0.5 microseconds. So when microsecond goes up, it will become megahertz. 1 over 0.5 megahertz, which is nothing but 2 megahertz. So this is the answer. Note that I'll again emphasize that we are interested only in counter type ADC. The question is silent. The question does not say which type of converter is there, but we'll assume, because it's the simplest of the ADCs that we know. So we'll simply assume that's the counter type ADC, in which each step, in order to climb each step, you require exactly one clock cycle. Okay. Since you have to climb 2 to the power n minus 1 steps from here to the maximum conversion, the maximum count that you can do is from 0 to 2 to the power n minus 1. Simply, the maximum value that you can count is from, let's say, from Vmin to Vmax. That's it. Nothing more can be done. This means you have to climb from 0 to 2 to the power n minus 1. This means 2 to the power n minus 1 steps, and each step takes one clock cycle. So total time taken is 2 to the power n minus 1 times t clock, which is also written here, and which has been given equal to 32 microseconds. We simply find out the value of time period of the clock, which is approximately 0.5 microsecond, and thus the frequency is nothing but the time period inverted, which then comes out to be 2 megahertz. Okay, so yeah, so that is all that I needed to talk about A to D converters. So if you have any doubts, any comments regarding this or J-gate flip-flop or ripple counter that we saw earlier, the toggling condition, so please ask. Today's class we focus mainly on the sequential circuits, and not circuits but their applications, to be more precise. We first saw the counters, in which the JK was always 1 1, so it was in toggle mode, and later part we saw that how are A to D converters implemented, not implemented, how are they used. The three figures that we saw are resolution, the step height, and finally the time period of conversion. So that's it from my side. I request if you have any doubts and any comments, then please come forward and ask. Anything? Okay, it's fine, it's okay. You can always email me. I have given you my address. I'm writing here again. I'm sharing, in case you don't want to ask in front of other people, or for that if you want to ask anything else, right? Okay, so with this our sessions, we for the past 3 weeks we have been talking about digital electronics. Now that part is over. From the next week onwards, from the next 3 weeks in fact, we'll be talking about diodes and BJTs, and finally field electron transistors, MOSFETs to be more precise. So I request you that please do some preliminary studies, like what is a diode, what's its symbol look like, what is it typical characteristics, input output characteristics, IV characteristics, sorry, forward bias, reverse bias, what is a BJT. I'll be going through the theory, but I'll be doing it like in 5 or 10 minutes. So it's better, you'll be able to understand it better, and you'll be able to ask questions or clear your doubts when you have done a bit of the study yourself. So that will really help you. Obviously we'll be solving the questions from the previous year gate examination. That's a main agenda. So okay, yeah, that's it. If you have no questions, then I guess we'll wrap up and see you next week. No doubts?
Thank you, sir.
Okay. Thank you. Welcome, Rajiv. Good night, everyone. Stay safe. Bye bye.
Good night.
Thank you, sir.
Yeah, welcome. Welcome, Aishwarya.